All right, guys. So again, as I mentioned, inverse functions and the original function together, they are two sides of the same coin. So it's like heads or tails. So when you look at root of x or at x squared, those are very much, geometrically speaking, the same function. Okay. So for instance, right now we are going to specialize for the differentiation of logarithmic functions. So for instance, here is how they appear to be the same function. You see that I drew here the graph of y equals to e to the power of x. It looks roughly like this curve, right? And it's a one-to-one curve, and therefore it is invertible. Now, what you see on this graph is if you imagine that it's free space and there is no gravity, there is no different sense of up and down. So this astronaut, he's walking on an axis that was arbitrarily decided to be labeled by the letter x. This astronaut will look up and he will describe this curve as y equals to e to the x. On the other hand, his friend, who is walking on the axis labeled y, when he looks up, he describes the curve ln y equals to x. For him, the x-axis is the dependent variable, and he sees the inverse, the opposite, ln y equals to x. Okay, and then when they try to communicate about differentiability, they are basically saying, okay, at this point here, is the graph linearizable? Does it look like a line if I zoom in? And of course, the answer is for both of them, yes. But they will not both agree on the calculation of slope. So they will not calculate the same derivative. So at the point x, the astronaut on the x-axis will calculate a slope dy divided by dx, right? And dy divided by dx is just the derivative of e to the x. It happens to be e to the x. So far clear? Now, the person on the y-axis will calculate an entirely different slope. The slope calculated on the person for the y-axis will be, I mean, he can borrow the slope of this guy and just write 1 divided by it. Why is it 1 divided by it? Because you see, slope is vertical by horizontal, but they don't agree on what's vertical and what's horizontal, right? So for the astronaut on the y-axis, the vertical is dx and the horizontal is dy. So he would say the slope is dx over dy, which is the reciprocal of the slope calculated by the astronaut on the x-axis. So the derivative of logarithm of y is 1 over x. Do you understand that? You just borrowed the calculation made by astronaut on the x-axis and wrote 1 divided by it. But it's not polite to answer the question when you take the derivative of ln y, the answer should be in terms of 1. So if I say the answer is 1 over e to the x, the answer is not in terms of y. So I make yet another adjustment and I just recall, what is e to the x? Oh, e to the x is y. So the answer is 1 over y in terms of the y-axis, okay? So geometrically, if you realize what I just described, there are fewer questions, there are fewer functions to consider. So if you started thinking about sine and inverse sine, as we are going to do today, you will see that they are essentially the same function, right? For thinking of it geometrically, they are two sides of the same coin. Good. I will. So let's just do the derivative yet another way, because some of you might find my wording convoluted. So you can use implicit differentiation. So for example, suppose that I asked you to find the derivative of ln of x. How will you carry out this calculation? Right here, I carried out geometrically. Instead of calculating the derivative of ln x, I calculated the derivative of ln of y, and I found it's 1 over y. And since letters are just arbitrary, derivative of ln x will be 1 over x. But here is how the same procedure. It's exactly the same idea, just with somewhat lesser insight. To find the derivative of ln x, I set y equal to ln x. And then I take e of both sides. So e to the y is equal to e to the power of ln x. Yeah? And what is ln x? It's the power that when placed over e will give you x. So e to the y equals to x. Yeah, so when I take the derivative, I do that by implicit differentiation. So y is this original function whose derivative I don't know, so I just write y prime whenever I take the derivative of that function. By chain rule, it's e raised to a power of some function. So the derivative will be e to the function multiplied by the derivative of the function, which will be the derivative of x, which is equal to 1. And then solving, I get y prime equal to 1 over e to the y. Very similar to what I wrote over there. And then I have to answer it in terms of x. What is e to the y? Oh, here it is. E to the y is x. So that's just 1 over x. You understand?
Yeah.
Great, that's brilliant. So the answer to the derivative of ln x is 1 over x. And that's not surprising, right? That's again, it's why is it 1 over? It's because the 1 over, geometrically, the insight is that the vertical and the horizontal, they switched. It used to be the y was vertical and x was horizontal, and then it switched. So here is another derivative. Again, remember, how do we take the derivative of a general logarithm? So this is logarithm base a of x. And I do the same thing, right? I set y equal to it. Y equal to it, which means now I want to take the inverse. So I take a to the power of y will be a to the power of log base a of x. By its very definition, when I take a to this power, I'm just getting x. So I have a to the y equals to x. So far, so good. And here I wrote extra steps in case, let's say, you forgot how to take the derivative of a to the y. Now, so I prefer to have e at the base. So a to the y is e to the ln of a to the y. By the properties of logarithms, I can take the y and put it in front, and I have e to the y ln a. And when I take the derivative of that, I get the original expression, e to the power, times the derivative of that. What's the derivative of y? It's y prime. And ln a is just a constant. So the derivative of the power is just ln a times y prime. And then I just put everything back in the way it used to be. So what is this guy? This guy is a to the y. So I have a to the y ln a times y prime is the derivative of x, and the derivative of x is 1. So I have this expression. A to the y times ln a times y prime is 1. So that means y prime is 1 divided by everything else. And then all I have to do is I just have to replace the expression in terms of x. What is a to the y? It's a to the y I see over here is just x. So it's 1 over x ln a. Okay? So logarithms, what we do, that was in some sense what we covered in the very last lesson. But what we do now is we address the problem of finding derivatives of something that you might have done without logarithms, but it would be pretty ugly. Suppose that you were asked to find the derivative of this expression. You see, there is a lot of roots, a lot of multiplications, a lot of powers. So if you did it directly, you would use quotient rule and then a bunch of product rules and then a bunch of chain rules and whatnot. And that's pretty tedious. So we might think to do something entirely different. So remember what we observed. We know that logarithms have those properties. We learned it somewhere at the beginning of chain rule. Logarithm of a product of two numbers is the sum of the logarithm. Logarithm of a quotient is the difference of logarithms. And if I have logarithm of a number to some power, I can move that number in front. Okay, we verified all those properties some few lessons ago. Good. So here is how we can figure out what to do here. So we set y equal to this expression which we want to differentiate. And instead of directly doing differentiation, I apply logarithm to both sides. You see, logarithm, applied logarithm. And why I do that is because the logarithm will allow me to simplify what I see over here. Now, what happens? Now, this will be logarithm of top minus logarithm of bottom, and then I break them further, and I use the power rule, right? So what you have is, look at it. Logarithm of the top is just, I take the 1 over 7, I put it in front, it's ln of this expression, plus 8 put in front, ln of x plus y, plus 1, sorry, minus everything on the bottom, I can move the 6 down, basically I have this expression that I get. Okay, I apply so that's subtracting applied logarithm.
Professor, the reason why you put a minus is because of the quotient rule. Because
of the quotient rule, right? So I will give you another exercise where we'll go slower. I just apply rules 1 through 3 recursively until I break it down, right? So first it will be numerator ln of numerator minus ln of denominator, and then I continue applying the product rules and then the power rules. So I apply rules 1 through 3. And when I do so, I reduce the expression to what you see over here. It's 1/7 logarithm of x to the 4th plus 25 plus 8 ln of x plus 1 minus 6 ln x minus 100 ln x squared plus 1 minus 5x. And then I take the derivative of that. It's much simpler. Now, what's the derivative of that? So let's look at it. So the derivative of the first guy, it's 1/7. Then we have logarithm. Derivative of the logarithm is always 1 divided by what you see in the denominator, right? What you see here, so x to the 4th plus 25. So it's 1 over x to the 4th plus 25 multiplied by chain rule by the derivative of what's inside of ln, which is 4x cubed. Then I'm done with this part. Then the derivative here, it's 8 multiplied by 1 over x plus 1. The derivative of x plus 1 is still 1, so no change. Then yeah. Yes. So what's then? Then I am up to, so I take the derivative of 6 ln x, that's just 6 1 over x. The derivative here of minus 100 ln of x squared plus 1 is minus 100. On the denominator, I get x squared plus 1, and then I multiply by the derivative of what's inside, which is by 2x. And the last is just minus 5, right? So that's what I get if I differentiate the right-hand side. If I differentiate the left-hand side, notice it's ln of y. The derivative of that is always 1 divided by y times y prime. It's the derivative of this, which is 1 over y times y prime. And y prime is what I truly seek to find, right? Y, this is my original function. I want to find what's y prime. So all I do next is I multiply everything by y. So I have that y prime is equal to y multiplied by what we just calculated. And I forgot to finish writing it. Y prime is the original expression multiplied by what's in the parentheses. Okay, so there is a typo here. You see, this is not y prime. This is the original function. That's just y multiplied by what you see here in the parentheses.
Isn't that the original function?
Yes, that's the original function multiplied by the derivative of the right-hand side. So I forgot to copy again what you see here in the parentheses. So it should be this. That's what y is multiplied by this. Yeah.
Okay. Yeah, I understand.
Good. Cool. All right, so here now it's your turn. See how fast you can do it. So here is your function. Y equals to x to the power of 3/4 root of x squared plus 1 over 3x plus 2 to the 5th power. Okay, please go ahead and calculate. I want you to find the derivative.
Is that 3 to the 4th?
It's
3/4?
3/4, so it's x to the power of 3/4.
How long are you giving us?
Well, see how fast you can do it.
Can I give it a shot?
Yeah, describe what you are doing. In other words, yes, go ahead.
I think I did this completely wrong, but I'll give it a shot. So, I started by doing ln of y is equal to 3 over 4, 3 over 4 ln of x plus 1/2 ln of x squared plus 1. And then because of the quotient rule, it's minus 5 ln of 3x plus 2, right?
Brilliant. That's wonderful.
Okay, so I don't know if I got this part correct at all. So then I have to do, then we have to do the, then we have to find the derivative. We're going to use, so y prime, right? You go straight to y prime, or do you do something else?
Well, so tell me what you do. So you took logarithms. If you take logarithm of the right-hand side, you took the logarithm of the
left.
Yeah. Of the left, right? So, it's whatever.
Yeah. So then it's gonna be from for the first, it's gonna be y prime equals 3 over 4 times x, or 1 over x.
The derivative of ln x is 1 over x.
Okay, yeah. So hold on, let me see if I got that. Yes, plus 1 over 2 times 2x over x squared plus 1 minus 5 times 3 over 3x plus 2. That's what I got.
That's
that
brilliant,
part.
Right? Do you see, guys, everybody, why do you get this part, right? So why is it 2x over x squared plus 1? That's because when you take the derivative of logarithm, that's you apply chain rule. So first it's 1 over whatever is inside of the logarithm. So when you say derivative of ln x is 1 over x, what you're really saying is the derivative of a logarithm is 1 divided by what's inside, multiplied by the derivative of what's inside. And the derivative of what's inside is 2x.
It's going to be 2x, right?
Right.
So, and then you get the same thing. It's going to be, for the next one, it's going to be, it's over there already. Minus 5 times 3 over 3x plus 2.
Right.
And then the next part, what you're doing is simply, you're just combining, no?
Well, you don't need to do more than is required. This is only, your goal is to just differentiate at the moment, right? There is nothing you want to do with the expression, so don't do more than you have to. Yes. So then notice that what we have on the left side is 1 divided by y times y prime. And our goal was to find y prime. So then what you do next is you multiply both sides by y. So your derivative is what was on the right multiplied by y. And what is y? Y is the original expression. So the derivative is the original expression multiplied by what you obtained on the left. Make sense?
Yeah. So I got everything up until that last part on the bottom of the screen.
That's good.
I have the same problem. I got stuck after that. I did not know what to do after multiplying by y prime.
Well, you multiply by y, not by y prime. You have 1 over y multiplied by y prime. Why? Because that's the derivative on the left. On the left, I have ln, and what's y? Y is this function which you're trying to differentiate. So you differentiate it symbolically, right? It's chain rule here. It's a symbolic chain rule on the left. So it's the derivative on the left is, when I take derivative of ln, it's always 1 over what's inside ln. Right? And then multiplied by the derivative of what's inside, which I cannot solve because that's what I might try to do, right? I'm just writing symbolically times the derivative of what's inside. And so the derivative of what's inside, which is what I really want to find, ends up being y multiplied by the derivative of what we wrote on the right. Make sense? So that's logarithmic differentiation. A few technical remarks.
I think we did this in, I think I did something similar in pre-calc.
Why not? You might have.
Oh, actually, yeah, I remember when we applied. It's I got this. That I remember this. It is implicit that y is greater than 0. I think I remember something similar.
Right, and not again when you carry out an operation, logarithms are not defined for negative numbers. You know that because you cannot get, let's say, e is a positive number, and there is no power to which you can raise e to get a negative number. So logarithms cannot be defined for negative numbers, at least not in our sense. It's not true that they cannot, but it's true that no real value of logarithm can be made to produce negative numbers. So technically speaking, when you apply logarithms, you are assuming that the expression to which you apply the logarithms is bigger than 0. Okay. Another thing that I can show you using logarithmic differentiation. I'm not sure if you would appreciate what I would say, but I will try nonetheless. Okay. So you see, we had this issue of taking the derivative of x to the power of alpha, where alpha is a real number. And you know that the power rule, is to drop the alpha and then to write alpha minus 1 as the power of x. Okay, this we proved actually only when alpha was either 0 or 1 or 2 or 3 positive integer. We possibly could extend it to roots, but in essence, we have not established it for a generic alpha. Okay. So the way you another problem is, of course, you might know what it means to take x to the power of 2. X squared, it's just x multiplied by itself. X by x. X cubed is x times x times x. And presuming that you understand how products work, you can carry out the operation, right? But what would be the meaning of x to the power of pi? What does it mean? Multiply x 3.1415, etc. times by itself. It's very ambiguous. What does it mean? The meaning assigned to x to the power of pi, what it means e to the power of alpha times ln x. And the reason that would be a kind of a nice definition for x to the power of alpha, it's because, you know, logarithms have the property that I can carry out and put the alpha here. And that would be e to the power of ln x to the alpha, which is just x to the alpha, whenever that makes sense. So, for example, what is x squared? X squared can be also written as e to the power of ln of x squared. You're with me, guys, right? So x squared is also e to the power of ln x squared, because e and ln, they cancel each other out. So when I introduce them, I'm not changing the meaning, correct? Let me write it in case you don't see it visually.
Because I'm not understanding what you're saying.
We have that e of ln x squared, right? That's the same thing as x squared, correct?
Okay, yeah, that I get.
Yes, and this part I can also write as simply e to the power of 2 ln x, because logarithms have this property that they can move the power, right? So this e to the power of 2 ln x actually means the same thing as x squared, correct? So why am I using this idea? Is because, for example, if I want to understand what is x to the power of pi, right? X squared, I understand. I know that it's just x multiplied by x. Presuming I know multiplication, I understand x squared. Yes. Yeah. But x to the pi, I do not understand. I want to possibly come up with an interpretation of what's x to the power of pi, and because for any x to the n, I can use this definition as, let's say, x to the n is just e to the power of n ln x. Okay. And that meaning I understand as x to the n. So I would assign the meaning of x to the pi to be e to the power of pi ln x. And in general,
it's one interpretation.
It's basically, it will make it unambiguous. And why does it make it unambiguous? One reason is that, if you remember, e to the x can be represented in terms of addition and multiplication. Of course, infinitely many addition and multiplications. But let's say e to the power of pi is not ambiguous like x to the power of pi, because what is e to the power of pi? If you were a computer, you would do the following. You would say 1 plus pi squared over 2 plus pi cubed over 6 plus pi to the power of 4 over 24, and in general plus pi to the n over n factorial. Which are all operations only involving multiplication and addition. Okay, so presuming that you can multiply pi by itself, some approximation of pi by itself, you can understand what is e to the pi. So what you do for all other exponents. You can understand them in terms of e. Okay. In essence, basically every thing of the form x to the power of alpha for any alpha, you can give it an ambiguous meaning by saying it means e to the power of alpha ln x, because you see you can if it makes other sense without invoking e and ln, and then you could just take alpha, put it to the power of x, and it cancels out and it becomes x to the alpha. You understand what I'm saying, right? I'm just extending the dictionary, right? X to the pi is something that when you think about it, you don't understand at all. Right? X squared you understand, x cubed you understand, and you realize that x squared, x cubed, and for any power that you understand, it ends up being equal to x to, let's say, n ln x. Okay, so then you extend the definition to all real numbers. X to the pi actually means e to the power of alpha ln x. Okay. So, for example, if I had to prove the exponential rules, the exponent rules, I only proved it for integers. I can prove it for all real numbers by understanding what is the exponential function, e to the x. And the way I understand it is that its derivative is equal to the function itself. That's the defining property of e to the x. Okay. So, again, guys, right? It's not a terrible crime if you do not understand me right now, but let me try to push this point. What is the derivative of x to the power of alpha? I want to show it's alpha x to the alpha minus 1, which is not a given if alpha is not an integer. We haven't proved it. So the way I do it, the derivative of x to the alpha is just the derivative of e to the alpha ln x, which is e to the alpha ln x multiplied by the derivative, which is alpha over x. Okay, so its derivative of the original function is e to the alpha ln x times the derivative of the power, which is alpha over x, and what I get is this. This is what. So if I don't convert it, this is e to the alpha ln x, and this part can be written as well, here is the alpha, I borrowed it here, but 1 over x is the same as e to the minus ln x.
Professor, someone asked, it's a good question. Abdul asked, are there other unambiguous things other than pi? Like, are there other things that have more than one set value?
Well, so what I see, first of all, let me try to understand. Pi, x to the pi is ambiguous, right? It's difficult to understand what is the operation that you're requiring to carry. What is x to the pi? What is x to the power of root of 2? Pretty much for any, not common number, it takes some strain to understand what it means to raise to the power of that number. Okay, and the exponential function e to the x, because you can understand it as an infinite polynomial, will allow you to figure out what's the meaning of all of them. Pretty simple, and it will allow you, in fact, to prove the different rules, right? So if you think about the exponential rules, when you figure out how to verify them, you verify them for integer powers. How do you verify them for non-integer powers? That's a different question. Okay. And you can use techniques of calculus to prove that power rules are ubiquitous for all real numbers. So, for example, if I have 5 to the power of root 2 multiplied by 5 to the power of root 7, that is 5 to the power of root 2 plus root 7 in the power, right? So, how do I know that? So, this is an example. So again, right, what I have here is that when I take the derivative, it's e to the alpha ln x multiplied by alpha over x, where 1 over x can be written as e to the minus ln x, and then I can prove to you that it's possible to add exponents, any exponents, when e is the base. So that becomes alpha e to the alpha minus 1 ln x, which when I convert it to my symbols is just alpha times x alpha minus 1. We can talk about it more, guys. I am pretty sure that a few of you are confused.
Yeah.
That's too bad. No. That's too bad. But 1 second, I'll just close the shutters and I'm with you.
Daniel, are you there?
All right, so we will return to that point if you care to return to that point. Let's for now talk about this, right? So those computational problems. All I want you to do is A through F. I'm not sure if we'll go through all of them. We possibly will select problem A. We might select problem F. I don't know, right? We will take we just need to find the derivative.
Problem B is very easy.
Well, let's start with problem A. I want you to tell me what's the derivative of ln of absolute value of x.
Well, if there's an absolute value of x, that okay, you want us to do it on our own?
Yeah, do it on your own, and then we will talk about it.
Are we finding the derivatives for all of this?
Yes, if you can do it fast, that's wonderful. If you're stuck somewhere, we'll go over it. But try to find the derivatives first through A, B, C, D, E, and F, right?
Yeah. Okay, awesome.
Right.
Professor, for the first one, there has to be two answers, yes?
Well, we'll see, right? Tell me, we'll just solve it, and then we'll work through it. Well, that's the question. I mean, does the derivative depend on absolute value? Absolute value changes when x is positive or negative, right? So we're trying to figure that.
Can I give it a shot?
Wait a few more moments, and I want to see that others solved it. And then, yes, you will give the shot for A.
Actually, if someone else wants to, I don't mind. It doesn't matter.
Well, most are quiet, and they're not showing their faces.
They don't have to show their face. They could stay if they want.
Yeah, of course. They don't have to show their faces.
I feel so stupid. I don't know how to do this. I feel so behind.
Well, it's okay. If you're when we'll do it, you will tell me where you're stuck, and if you're continue to be stuck, we'll talk more after class.
Okay.
Patel, did you by any chance get a chance? Did you get a chance to watch his lectures?
Yeah, I do that.
Okay.
But lecture 15 is not there, and I think that's the lecture 15.
What do you? I think it. Yeah. I finished watching lecture 14. I think it was. On implicit differentiation.
Right. Today I watched 16 because there is no 15.
There is no 15. Okay.
And in the end of 14, I think he started
covered. Yeah.
No, but not much. Only the first two questions that we did today are there.
What you do, guys, whenever you're stuck on a problem, right? So this is how I learned it, right? If you cannot solve the problem right away, what can you solve? What do you know? What do I remember about logarithms, right? That's how you get to be familiar with them. right? It's like with people, right? Do you know the person? Do you know what they like, what they don't like? You then begin to recognize them as your relatives.
Professor, okay, so there's essentially one answer for the first one because they're both the same in context of where x is negative.
Yes. So, for instance, right, 1 over x is defined for x negative and x positive, but logarithm is only defined for positive x. So if I take ln of absolute value of x, then I make it, you know, ln of absolute value of x, I make the function. Yes, go ahead.
Is it?
Yeah, I'm sorry, I lagged out. My mistake got kicked off. I missed what you were saying.
Yes, okay. Can you hear me now?
Yeah.
Yeah. So what I said is this. I said that ln of absolute value of x now is defined for x negative and x positive.
Right.
Just like 1 over x is defined, you see? So when I take the derivative of ln of x, I get 1 over x. But when I do that, I'm assuming that x is positive. Now, when I have ln of absolute value of x, I no longer have to assume that x itself is positive. And here is how we solve it, right? So what is y? Y is really a piecewise function. It's equal to ln of x if x is positive. And it's equal to ln of minus x when x is negative, right? So when I see absolute value, I remember it's just a piecewise function. It means two different things. It means nothing done. The absolute value can be dropped and it disappears if what's inside is positive, or you replace the absolute value by -1 if what's inside is negative. So we have this two, right? Now, what's the derivative in the event x is positive? In the event x is positive, I'm just taking the derivative of ln of x, which is 1 over x, which is, you know, what I'm familiar with. Now, if x is negative, I'm taking the derivative of ln of minus x, yes? Which is what? Which is now it's chain rule. Now on the bottom I have minus x, and the derivative of minus x is -1. So I still get the same thing. I get 1 over x.
That's what I got.
Good. So it means that the derivative of ln of absolute value of x for any x, positive or negative, will just be 1 over x. Good. So now if you understand this, guys, see if you can solve b. Take the derivative of y, where y equals ln of absolute value of sine.
Well, if you just take the simply, isn't that the derivative of cosine x over
Sine of x? No.
What, Sarah? What did you say?
I was talking about the first one before. I only got 1. I didn't get the over x, and now I realized what my problem was. I forgot. Yeah, I forgot to.
And since you mentioned 1, guys, suppose you found that the derivative of some function identically equals to 1. So you had some, let's say, some function f of x. You took the derivative, and you get the answer is 1. What is the function?
The answer.
What's the function? If you say I didn't tell you what the function, but suppose you carried out, you differentiated the function and you got as your answer 1. What had to be the function?
X.
Beautiful. It had to be x or x plus 5 or x plus 7. You cannot determine precisely, but you are certain it was a line, and the slope of that line as measured by your coordinate system was 1.
Correct.
Correct. And geometrically, you see, I mean, although you have x or x plus 5 or x plus 7, those are different descriptions of different lines.
Right.
But geometrically, right? If you move a line up or down, turn it around, it's the same thing, right? If the derivative equals to 1, then you are dealing with a line. From a geometric point of view, there is only one line. You understand? From coordinate point of view, there are many lines. There are lines with this slope, lines of that slope, no slope. But you see, so sometimes geometric point of view makes things very, very simple.
Right.
Right. So since logarithm cannot possibly be a line, you've seen the graph of e to the x, you know that it's impossible that its derivative is constant. Yeah, brilliant. So the answer is 1 over x for all of them. Okay, and then for b.
Okay, fine.
Cool.
I got it. Okay.
Beautiful.
For b, it's going to be
it's going to be cosine x over sine x.
Beautiful, right? So when I take
Which
the
is
derivative,
equal to cotangent x.
yes, beautiful.
Also, you can write it two ways technically then.
You can write many. Oh, the answer can be written in so many ways, right? It's either, but you can still, in theory, tell whether it's correct or not. So, by taking the derivative, I just have 1 divided by. You see what happens? I just verified from A that if I have ln of absolute value of something, the derivative will be 1 divided by the something without absolute value, right? And then multiplied by the derivative of what's inside. So you see, the derivative is 1 over sine multiplied by cosine, because that's the derivative of the bottom, which you can recognize as cotangent. Cool? Yes. And then how can I solve C? What's the derivative for C? That can be done very fast. No.
First, you're going to want to do, you're going to want to take you're going to take the x in the exponent for e to the x, and you're going to put it in front of the log, right?
Yes. Yes, and that makes it very, so yes, you can write, Abdul, just like what Joel said, you can write x log 3 of e, correct? And then what's the derivative?
Over d to the x is equal to x. No.
So what's the derivative?
The derivative is simply just going to be log 3 to e.
Log 3 of e, precisely. And what sort of curve? I'm not asking you to be too precise, but y equals log base 3 of e to the x. If you had to trace with your finger the shape of this curve, what would you do? In other words, I'm asking you to recognize this curve. You know it.
Is it not simply what we saw before in the first?
Well, and then without obfuscatory language, precisely what is it?
1 over ln 3?
No. That is just a number. I'm asking you, what is this object, right? If you were to pet it. If you were to pet it, what would you feel? What are you petting? Right? It's not if you're petting something fluffy like this, I ask you what are you petting? You tell me a kitten. You don't tell me it's a kitten that has a black spot of radius r, right? You don't give me a complicated description. You just tell me kitten. So what is this that you're petting?
Straight line? I don't know.
Exactly, straight line.
Oh my
Beautiful.
God, okay.
It is a straight line. Why? Because look at it, right? You got the derivative is this. I'm not sure what this number is. I can use a calculator to estimate it, but right, it's the number that if you place over 3 as the power of it, also you will get e, right? If you place this number on top of 3, you will get e.
Okay.
Right, but that means that that's a constant number. It has a constant slope. So this creature, this curve has a constant slope. If it has a constant slope, it must be a line. Right? It doesn't matter the constant slope. If the constant slope is 5, it's just you're looking at a line at an angle, right?
Okay.
Right? But geometrically, there is just one line. Cool? And do you want me to solve or do you want to discuss solution of any of the remaining problems or anything here? Because it's essentially it's the same thing. Would you like to talk about any of?
Can we do D with you? But can you do it step by step, like I'm disabled? Okay, step by step, because I really don't understand.
but
אני לא מבינה, אני לא יודעת איך.
Okay, יש לה שאלה, בוא ננסות.
Okay, so we are doing D, right? D step by step. Okay, so first of all, I don't have to necessarily do it if the function is still simple. I have sine multiplied by a ln of 5 times x. And because it's a ln of a product of two numbers, I can write it as a sum of two numbers. You see what I'm saying, right? So it used to be this, but I can say it's a ln of 5 plus a ln of x. That's a property of logarithms. And I went over it. You might have not been there. I don't remember. It was when I talked about chain rule, and I have it in my notes at least. Yes, so it's sine of ln 5 plus ln x. And then when I take the derivative, it's just product rule. You see, it's sine multiplied by this. So the derivative of sine is cosine. And I didn't want to write the parentheses then. I just wrote it as ln of 5. I just combined it. So this is just ln 5, yes? And then plus, now I keep sine, I don't bother him, and I take the derivative of what's in parentheses. So this is a constant. The derivative of a number is 0, plus the derivative of ln x is it's always 1 over what you see inside of the logarithm. So it's 1 over x.
Yeah.
And that's over, right? That's it. It's just the derivative of logarithms is 1 divided by what's inside of the logarithm, and by chain rule multiplied by the derivative of what's inside of the logarithm. But of course, the derivative of what's inside of the logarithm is just 1. Good?
Yeah, and f is the same thing that we did earlier.
Yeah, so when you here you already have a logarithms, right? So remember, if you do not have a logarithm in front of an expression that has lots of multiplications, quotients, and powers, you want to place the logarithm in front of it, okay? But in this case, we already have a logarithm in front, so we are just going to apply all the logarithmic rules. So for f, you see, before I take the derivative, because I don't want to deal with the derivative of what's inside, I'm going to use properties of the logarithm to write it as this, right? So it's 5 ln of 2x plus 1 minus 1/2 ln of x squared plus 1. Where you see what I did?
Professor,
yes.
Yeah.
Continue. I'm sorry. Continue.
When I have ln of numerator minus ln of denominator, and when I break down the ln of numerator, I use the fact that I can take the power and I move it in front of the logarithm, right? All right. So when I digest this entire thing, when I break it up, I have this expression, and I differentiate this expression. How do I differentiate f? So it will be derivative of y is dy dx. And then here I have 5. The derivative here is denominator is 2x plus 1. The derivative of what's inside is just 2. So it's 2 divided by 2x plus 1 minus, in this case, it's 1/2. I put when I take the derivative of logarithm, I just write 1 divided by what's inside of the logarithm. So it's 1 divided by x squared plus 1 multiplied by, yes, go ahead.
The numerator 2.
The numerator, no, the numerator is not 2, but it's x squared, right? So it's, yes, I was worried I made another mistake, but no, it's 2x, because the derivative of x squared plus 1 is 2x.
Okay.
And of course, then I can cross out the 2's here, and I can write it as simply 5 times 2, which is 10 over 2x plus 1 minus x over x squared plus 1.
Okay, that was fun. Okay.
Good.
Yeah, this isn't that trivial.
We made it. We made it. Okay, trivial.
No, it's whatever. I don't want to be pompous. When is the next test?
It's coming soon. I can already post it now. There is no problem about it. I might very soon switch to integration and leave you with difficult topic, which is what you call it, which is optimization. Since really 1 hour, 2 hours, or many lessons usually do not suffice. It's some of the hardest topics are, I would say, related rates and optimization. I think I will cover related rates, and optimization is in my videos, and it's in general, right? From my experience, I never have more time than one session to cover it, and that one session is almost like nothing.
Related rates is pretty comfortable. You need to come up with like formulas yourself. I'm like,
yes.
Yes,
you need to come up. That's the problem. There is that you need to come up with formulas yourself, which is in fact what's the entire thing useful for, right? So what we're doing here, it's really just well, it's tedious because we're just practicing rote differentiation. That's not how problems come around. I will show you at least a few. So, for example, related rates is one of the main ways in which calculus is used in basic physics. Because yes, because you
I have to.
I have to know that cold.
Sorry?
That's okay.
Okay.
It's okay. I have bad connection.
Yeah, bad connection. It happens. Yeah. So hopefully mine is not terrible.
I have another question.
Go ahead.
What will we be taking the test on? I think I heard someone say that it's gonna be online.
Well, my understanding, and that's only my understanding, right, is that you see, mini calculus courses are what do you call it? They are departmental. In other words, if you were registered in a morning course, then it's a departmental final. Right. But if you're registered in my course that has been over the years through, then it's my final.
Right. Is that easier or harder than the?
I mean, honestly, the way my class is running, that's why so few people are also coming, is that from the point of view of surviving this course, it's a joke. It's so easy to just you take your time. You know, you don't have to be fast. I'm not even sure you have to be anything. If I were, you know, I would be able to cheat on this exam in so many ways. People were able to cheat on my exams even without, well, with me present in the class, actually. Right?
So teach us how. How can we cheat?
How can you cheat? Know. Well, it's good. It's good.
That's legit.
Cheating is the thing is which I still haven't implemented for several reasons. First, I actually don't really want to catch you. It upsets me, right? And it's also I cannot necessarily catch a person and be certain that they have copied or not copied. I can certainly catch a person and be certain that they don't know the material, or at least don't know closely to what I want. And I think most people in this course don't know it nearly to the level I want them to know it. Right? So yes, and with goodwill. I mean, that's the thing. This class feels to me, it leaves me always very upset. I feel like I'm engaged in as a rapist, like I'm engaged in some sort of rape. I'm teaching something that people don't want, don't need, are not interested in, and you know, what am I doing here? With advanced mathematics, usually it's a facilitation. I mean, they're enjoying it, and I enjoy it therefore even more. So as long as you have goodwill, it's easy to teach you. I can teach you this material better than, well, any subject that you will take. I think it will be something that you know if you want it. But if you don't,
I miss the class, the actual class, coming to class.
But you understand that anyone here is able to see me in person, in flesh, if that's what you want. Because, you know, I mean, what I think about the entire thing that they're doing. I think they're morons, right? And the fact that they're scaring you by numbers doesn't matter to me, right? Besides, if you know the Russian expression, we do not stand for the price, which means we can take as many casualties as required. We don't care.
We don't care.
Yes, I am easily able to lay my head for the purpose of mathematics.
Wow.
Well, it's a joke, since I mean it's really silly. And, you know, my God, people have gotten so soft. They think this is the plague.
I think this is the plague.
You know, you have to be. If you saw my video that I sent you, right, or you read the quote, it's Pushkin wrote a very beautiful poem about the plague.
Didn't Pushkin die? He killed himself or something?
No, he didn't kill himself. He was shot in a duel.
The Russian roulette, right? Or something?
No, he was shot in a duel. In other words, he fought in a duel, and his opponent shot him. It took him 3 days to die.
It took him 3 days to die.
Yes. Right. So let me go back to the material. Although obviously I want to talk to you about Pushkin or quote something from him. But let's talk about derivatives. So what I want you to now do, and to the best of your ability, solve questions A, B, C, D, E, and F. And your goal is to take the derivative.
What?
So you see, I don't need to be fancy.
Oh, we did this before. Yeah. This is simple.
Yes, some of them are simple. Okay, so take the derivative of A. We are comparing derivative of A, derivative for B, for C, for D, for E, and for F.
Would just be opposites of each other, no?
Well, A is going to be A times X to the A to the negative A to A minus 1.
Exactly, right? So derivative for A is trivial. Yeah, so one second, Joe. Let me. I know you understand it, some of it, but
I'll shut
be
up,
sure
I'll
that
shut
all
up.
of them do, right? So take the derivative A, B, C, D, E, and F as quickly as you possibly can, please. And by the way, Darnell, noticed that you joined. Glad to see you, or to hear, or to imagine that you are here. If you are here, of course.
Yes.
Good.
Can you hear me?
Yeah, I can hear you.
Yeah, I've been here. I've been here.
Good.
All right. I got here about like 6:30. A little
I
late,
know.
my
That's
bad.
okay. No worries. Again, guys, when you are not coming to class, it only bothers me only in one sense. When I think that you're not coming to class and that you don't give a damn about the material. You could kind of not see me, but care about the material, know it, then I'm fine with it. But if you, I just imagine how you just don't care about the material, I get red angry.
Yeah, I think I messed up.
Let's first solve A through C, and then we will move to the other three so that it's not too boring for all of you. No, you only take the derivative once for E and for all of them. I just want you to take the derivative once for all of them.
I'm lost.
Yes. But where are you lost? Starting from which problem? I think you lost
On
connection.
C.
C. Okay. Think about it, right? What bothers you about C? And how could you remedy it?
Why isn't it
I
just
skipped B because
One
I
second,
don't know.
Joel. Oh, I want to hear what Sarah was saying. What Sarah? What were
why
you saying?
isn't C just 1?
The derivative of C just 1. Then you are saying that x to the power of x is a line. Does it look like a line? Could it
No.
possibly be a line? So it cannot
No.
possibly be 1.
1 over x?
1 over x. If it's 1 over x, you might imagine that the function is similar to a logarithm, and that's not likely.
Ugh.
All right, we'll do it. You see, guys, that's what I mean. How do you attack a problem here? First, try to recognize your previous friends. Why is it that you're able to take derivatives of other guys? So Abdul says 2 to the power of x times x to the x minus 1. It's close, but that's not right. So what bothers you about this function? Look at it. The reason I wrote a, b, and c, they get more complex in progression, right? So this here, you have a variable base and a fixed power. And Joel said the way we differentiate is we drop the a, and then multiply by x to the a minus 1, right? So this one we dealt with almost from the beginning of class. This is the reverse situation. Here we have base is fixed, power is changing, and in this case the derivative is what? What's the derivative for b?
X to the a minus 1?
No.
Sorry, whoops.
No.
What's the derivative of a to the x?
I got a to the x times log of a.
Precisely. All right. So the derivative
I
of.
don't even know how I like.
Yes.
Can you explain why? Like, I don't even know why I got that.
Yes, guys. I see one thing about so right now we have limited time, so I'm explaining it. But here is another thing. You should struggle to explain it to yourself. Understand it. Why is it working? Go back to the definition. See what you can say from there. Go back to other ideas. So how does b work? Well, why is it a to the x ln a? Well, first of all, if it were e to the power of x, what would have been the derivative? E to the power of x, what's the derivative then? Guys.
E to the x.
E to the x. You see, you right away tell me the answer. That means that if e were here, the question would have been simpler. So why not imagine that e is here? What do I do? How do I imagine that e is here? Right? In other words, I look at it and I say, I don't like the question. I want this question. And then the art is to convert what you already have here to something that looks like e to the x. I call it wishful thinking. You understand? So first of all, can you recognize a problem that seems similar and its derivative you know how to calculate, but then that's your goal. You want to get from here to here. And how do you do that? Well, what is a to the x? That's the same as e to the power of ln a to the x. Do you agree? Because e and ln cancel each other out, and then I can take the x and I move it down. So so that becomes e x ln a, right? And notice that it's not quite e to the x, but it's the next best thing. It's e to the x ln a, which means x multiplied by a number. What's the derivative here? The derivative will be the original function multiplied by ln a. It's and what is this? This is back a to the x, right? This is just a to the x. So the answer is a to the x ln a.
A to the x.
Yeah. Good.
Yeah, I did something totally different and got that also.
Well, I mean, one thing is people have good memory, right? Some have very good memory, and just you might just keep the fact and recall it for a while. But then the question is this, right? Well, how do you verify? If you have always tried to explain it to yourself or to somebody, if you can explain it, that's how you get to understand something. Explain it.
That's true.
So y equals to a to the x. The derivative is a to the x ln a. Okay. And what about c? Can you now help me solve c, please? So what's the obstacle, right? What I do not like here? I don't like that I have both variable base and variable exponent. So what do I do? What tool, think about, guys, what tool can I apply here to make the expression simpler?
You want to get ln of y.
Exactly, right? So you see how do you feel that ln would work here? Because ln will allow you to drop the power down. So I apply logarithm to both sides. That's exactly what I do, right? So I apply ln y, and that now creates ln x to the x, and that allows me to drop the x. You understand? Because I know what logarithm is, I'm familiar with its abilities. I'm able to make it my friend. I'm able to use it whenever it comes handy. So ln of y equals x ln x. Are you with me, guys? Everybody understands?
Yeah.
And why is it nicer? Because it's not as nice as differentiating just x or just differentiating ln x, but it's product rule, and I'm able to get by. So the derivative on the left-hand side by implicit differentiation is 1 over what's inside ln times the derivative, y prime. And y prime is what I'm seeking. Why is this? I want y prime, right? Y prime is the derivative of x to the x. So 1 over y prime, and then I apply product rule. So that would equal to derivative of x is ln x plus x times the derivative of ln, which is 1. So I get that the derivative is ln x plus 1. And then I need to multiply it by y, because my goal is to find just y prime.
I keep forgetting to do that. I got up to ln x plus 1, but I keep forgetting.
Yes, but do you understand why you need to do it? Because when you apply ln, you change the expression. You're now no longer differentiating y, you're differentiating ln of y. So ln x plus 1 is the derivative of ln y. So you multiply by y, and you get x to the x, ln of x plus 1.
You take I got it.
Cool.
I mean, I hope everyone else does too.
Yes, I hope so too. As you say, again, guys, believe me, right? You need to struggle with the material, and all you struggle is just figure out, well, first of all, the functions and their properties.
It's just confusing at the last part. Like, I get it, like y is equal to x to the x. And that,
right.
Yeah,
Sorry?
like, that's like, Sarah, I think you were saying the same. That you just take it from the beginning for when you multiply it by y prime, by y, you hear me, right? I'm not losing reception? Am I good?
I hear you.
So then you just take it in from the beginning that you just, because y is equal to x squared, x to the x, you just put it back in front of ln x plus 1.
Right.
All right, so let's see if you got to this lesson. So solve D for me, please.
Good.
And do it fast, guys, as we are approaching our end of lesson.
We have 25 minutes.
Well, I want to cover inverse trig functions.
Okay, so you want us to do F, you said?
Do D. Actually, do D, E, and F. I want you to solve all of them.
Okay.
But quickly do D, and we'll discuss it.
For this one, you also want to find ln of y.
Yes. Do you understand why you apply logarithms? Because it's like a logarithm is your friend. You know that if you apply logarithm to both sides, really you care about the right. The right side that allows you to move sine x.
Sine x to the bottom, yeah. X is sine of x.
Okay, I'm stuck, but I think I'm on the right track.
Okay. David Stein, you are strangely quiet.
Yeah, I'm here.
You want us to do all of them, or are we going to do
Well,
it one
let's
by one?
do D one by one so that we can get some progress here, right? So D, again, right? So the main idea afterwards is just tedious calculation. The main idea is apply logarithm to both sides, because then sine will be dropped, right? So it used to be ln x to the sine x, and sine now is dropped. And then when I take the derivative of the left-hand side, I get 1 over y prime. And here I apply product rule. The product rule will be derivative of first function, which is cosine. I don't bother the second function.
Right.
Plus sine not bother, derivative of ln x, which is 1 over x. So we get this, okay? And then I just multiply by y. And replace y by what it used to be. The answer has to be presented in terms of x. Y was the original expression. So it's x to the sine x times the derivative. It's always the case. When you use logarithmic differentiation, it's the derivative after you apply the logarithm of the left side multiplied by the original expression, the original function.
Can I ask something?
Go ahead.
So I'm kind of frustrated because I seem to do this. I seem to always miss the very last step. I got it to the second to the last part where it says x to the sine x of cosine x log x plus sine of x over x. You see what I'm saying?
Yes.
But I can't. I don't know how, like, for the next, like, I don't know why I just can't simplify it more narrowly to the last part.
There is no the last part. They just multiplied by y, which is the original expression. So it's
So
what you see in the parentheses. Don't forget. So don't forget this, right? You have 1 over y times y prime, and then remember that you are solving for y prime. You were asked to find the derivative of this function, which is simply replaced by y, right? So this is what you need, and that's why you multiply by y to get on the left you get y prime, and then here you have to replace what's y equal to. It's x to the sine x.
Yeah. But I'm not. But you see what's after that? Like, I don't like. What did you like?
You mean what I did here?
Yeah, because
I could have left it like this. So I could have left it like this. It's perfectly fine. What I wrote over here. Or what I just decided to do is to show you that, well, if you're interested, you can just move the. If you have cosine times ln x, I can move this as the power of x. I can move it and make it the power of x. It's just in case a solution is presented differently, you are able to. There is no need to do that. I mean, you could have left it like I wrote here.
So where you are now, you see where you are now, like where your mark is now.
Yes.
So if I wrote that as my final answer, would that be considered?
Absolutely, of course. Why is this more correct than this? There is no reason, right? Both are correct derivatives. It's just, for example, if you were having multiple choice and this was your answer and this was the multiple choice answer, you would have had to connect the two. You would have had to recognize that this and that are the same.
Indeed.
You see, that's all right? It's only to recognize that my solution is correct and the solution given by someone else, it's also correct. That's all. And then how do I solve E? E, I do it the same way, right? I apply logarithm. And what do I get? I get x to the power of x times ln E.
Right, same thing as before.
Right, so and ln E, I can simplify to 1, right? Because ln E is just 1. So now ln of y is x to the power of x, but I already solved x to the power of x. So perhaps that's what Abdul mentioned. He kind of said differentiate twice. That's not quite what happens, but I need to maybe take the space and do it separately. But I already solved x to the power of x. X to the power of x, my solution was the derivative of x to the power of x is itself multiplied by ln x plus 1. Okay, we already did it in part part C, I think, right? The derivative of x to the x is just x to the x times ln x plus 1. So now I get that 1 over y times y prime equals x to the x ln x plus 1. Good. And the other questions are of the same type. Right? Let's talk about derivatives of inverse trigonometric functions. Good. So first question that you should wonder about, okay, I'm saying inverse sine, but is sine differential? Sorry, is sine invertible? Is sine invertible?
No, I know because I watched the video.
No,
Now,
but
I will participate also with my notes.
sorry, you would participate with your notes?
Yes, I will answer everything with my notes.
No, no, what do you mean? I'm not sure what you mean by that.
Never mind. Whoever will understand, understand.
I understand.
You're giving me my own solution, like a feedback mechanism, but no, you don't need to. I'll answer with your mind.
It's not for you.
Okay, so Professor, we take our inputs into consideration here.
My question was this, guys: is sine x is invertible? But L said no, and she is right, but not because I said that she is right. Right? Why is she right? Why is sine x not invertible?
Can I give it a shot?
Go ahead.
Also, I'm on my phone, by the way, because I don't know if I'm freezing or not. Just by the way.
Well, so, I think you are on two devices. I see.
I am because I'm using my phone to speak, and right. I'm on the. Yeah. Okay. So.
Okay. Now I don't hear you. Maybe you froze.
No, I'm not talking. I'm like still trying to think.
Okay.
I'm thinking. I can't go for it. I'm sorry.
All right. What about you, Batel? You said no, but would you like to talk? Or Sarah, or who else is available? Or Zina, who wants to talk to me?
Oh, okay. Hold on a second. So the answer is no, right? I'm waiting. Watch how I'm waiting for you to say yes and that we're wrong. But
what does it matter what I say? I mean, guys, you're not trying to please me. You're trying to understand the subject. You don't have to agree with me. That's another thing. You don't need to agree with me. Let's say for many of you are quiet. I mentioned something about the plague. Maybe many of you are afraid of it and don't agree with me.
Give me a second, Professor. Give me literally 30 seconds.
Okay.
I think it should be inversible, right? Because you have two values and you should have to go back to the other value.
Invertible means that you can press undo, right? So,
no, it's not. I'm sorry. I'm sorry to interrupt you. No, it's not. It's not because it doesn't pass through the graph doesn't pass the horizontal line test.
Yes, that's right. And what so Sam and everybody else, you see, it does not pass the horizontal line.
So there. Okay.
But why does it? 1 second, Joel. What does it matter? So it doesn't pass the horizontal line test. So what? What is the idea? So some of you are studying computer science. To be invertible is the same as for you to be able to undo the operation. Right. So to undo the operation, you need to know what caused the situation, what button was pressed, so to speak. Right. So for example, where I drew the horizontal line, right, that means that if you put this input, you get this sign. If you put this input, you get the same sign. If you put
there's more than one.
There are more than one option. It's like with the Coca-Cola thing. Remember, if somebody is, you don't see what button they pressed, but you see that the output is a Coca-Cola. An inverse function will be to figure out what button was pressed, right? So given that it's Coca-Cola, what button had to be pressed? And that's not possible if there are many buttons corresponding to Coca-Cola. It's only possible if there is one button that corresponds to Coca-Cola. So for example, if you had 1 is Coca-Cola, 2 is Pepsi, 3 is Sprite, and 4 is water, then if you see Coca-Cola, you know the person pressed button 1.
But it's not 1-to-1.
Yeah, so it's not 1-to-1, right? So sine x is not invertible. And so cosine x is not invertible, and many of those functions are not invertible. So, but what you can do still, right, here, you see what I drew in red. You can define a function which I call capital sine x, and that's the restriction of the domain of sine. It's the restriction of sine to go between minus pi over 2 to pi over 2. And over this segment, the function is invertible. In other words, the general unrestricted sign is not invertible, but the capital sign is invertible because it's not the full graph, it's just part of it, right? So in other words, if you are told that the buttons pressed are between minus pi over 2 to pi over 2, then every y value can be reversed. I can figure out what happened here, because over this interval, sine is a strictly increasing function. So therefore, one-to-one function.
We're
Okay?
saying that if the inverse is also a function, then the function is
well, the inverse has to be a function, right? So so the horizontal line test is supposed to verify that it's possible to, you see, this is the output. This is my Coca-Cola can. What button was pressed? In general, it could be this button, that button, that button, that button. There are many buttons, infinitely many, in fact. But if I restrict it, look at it. If I restrict it, it must have been this button, right? So if for this capital sign, the only button that works is this one, because it's underneath the red part of the curve. Does it make sense? So basically, capital sine x is little sine x, but x is restricted to be between minus pi over 2 and pi over 2. Okay, I hope I haven't lost too many of you. And there, sine inverse is a function. Their sine inverse is well defined. Okay, and again, sine inverse is not so much a different function. You can see the graph of sine inverse by being astronaut on the y-axis, right? This astronaut, if this is your up and this is your horizontal, then you see the sine inverse function. Good.
Could you use sine inverse for other areas of the graph?
Yes, that's called the principal branch. So sine inverse is defined to be this branch, but of course you could have defined other sine inverses. Okay, it just, this is the standard. This is the principal branch, they call it. Okay, so that means that you can define many inverse functions. You could have defined this curve. You could have defined the curve somewhere here, or maybe even this curve. You could have defined many different curves. Okay, that's important to know. So in general, I will not keep writing. I will not keep writing capital sine. I will write it as little sine x, and by default, I will mean, whenever I talk about the inverse, I mean the restricted sign. Okay. And let's see if you can carry out very quickly the following calculations, guys. Tell me, please, what is sine inverse of 1? You see, so sine converts angles to ratios. So what is sine inverse of 1? Can you tell me? This is, in other words, it's asking, right? So what value is carried by sine to 1? Another way to think of it is what value is carried by sine to 1, and that value has to be between minus pi over 2 and pi over 2.
Everything.
Would it be pi over 2?
It's pi over 2, thank you. The answer is pi over 2. What's sine inverse of minus 1? You see, so I'm not sure how you look at this expression. What I see when I think of it, I say this is an angle. It's minus, yes, Millie.
Oh, it's the same. It's the same, just negative.
Yes, it's the same, just negative. So it's minus pi over 2. So when I see this, I'm thinking I am the angle carried to minus 1 by sine. That's what I think personally. And that's the undo of minus 1, because that brings you back to the angle, right? You see how it works as an undo, right? So I give you this value, and I want to know the angle. So this is saying the angle that's carried by sine to minus 1. What about C? What's sine inverse of root 2 over 2?
That'll just be pi over 4.
Precisely, that's pi over 4. What's sine inverse of minus 1/2?
Well, I'm not sure.
So what value it will produce 1/2 or minus 1/2 for sine? What angle? So you should.
Pi over. Oh, if it's negative 1/2 for this, it's going to be negative pi over 4, or is that no? We did
no,
that. No. That was no. It's negative pi over 6.
Yes, it's minus pi over 6. So this would be minus pi over 6. What about this? It's sine inverse of minus root 3 over 2. What's the angle? So wait, Joel, wait, I want to see if other people will answer. So what
I actually
is,
don't know. So
okay. There are only few angles to know, guys, which you should also know how to figure out. So what is all the value of trigonometric functions at pi over 4, pi over 3, pi over 6? And, you know, pi over 2 and pi and all that stuff. But essentially pi over 4, pi over 3, and pi over 6, just 3 angles, nothing more. So what is this?
Negative pi over 4.
No, it's root 3 over 2, not root 2 over 2. It's minus root 3 over 2.
oh, then that's
Sam, what is that, Sam?
So that's 60 degrees.
Yes, well, think in radians. And Abdul, you're right, it's minus pi over 3. Thank you. What about f? What is sine inverse of 5?
isn't there none?
Precisely, it's impossible, right? Sine only produces ratios between minus 1 and 1.
Minus 1 and 1, right?
And there is no angle that's mapped by sine to 5, right? This is saying I'm an angle that's mapped to 5 by sine. There's no such angle, so
Is it?
it's
don't we
undefined.
consider it to be right, undefined. That's
Right.
what I was,
And for other functions, you know, cosine is not invertible, but you can define capital cosine by restricting the little cosine for x between 0 and pi. That's the principal value. Of course, you can have other restrictions. That's just the default value. You have this restriction for secant, this restriction for tangent, and for cosecant and whatnot, right? So now the most interesting part, finally, of this class, and we have little time. I'll try to extend it. What's the derivative of sine inverse of x? It's just a derivative of another inverse function. We can do it either geometrically or by implicit differentiation. They mean exactly the same thing. The reason they work is exactly the same reason. So how do I figure it out? So I set y equals to sine inverse x. Yeah, y equals sine inverse x. And that implies that if I apply sine to both sides, then I get sine of y equal to x. Yes?
can you explain?
It's because the sine cancel the sine.
Yes,
inverse.
because the minus 1 and 1, they cancel each other. That's why
We
I use
didn't
the
write it,
symbol
right?
minus 1. But another way to think of it is also what is sine inverse of x? This is just saying angle that if you apply sine to it, you get x. So if I apply sine to y, I am applying to sine of this expression and I get x. It means apply sine to it and you get x.
I got it.
So sine of y is equal to x, yes? And then I use implicit differentiation. So the derivative of this side, I know how to differentiate sine. So the derivative is cosine times the derivative of the angle, which is y prime, equal to the derivative of x, which is 1, right? So we have that, and that's some of things that Bat-El was asking me, I think, yesterday night. So y prime is 1 divided by cosine of y. But what's cosine of y? Cosine of y is this thing. So it's 1 divided by cosine of sine inverse x. And this is, you know, you can simplify it. You can make it much nicer. What this means is the following. If I apply sine to this expression, this is just an angle. If I apply sine to it, I'll get x, but I'm applying cosine. What do I get then? So let me draw a right triangle. If this is the angle sine inverse of x, which means that in this triangle, if I apply sine to the angle, I'll get the ratio that opposite over hypotenuse is x. So I can set x as my opposite and y as my, the r as 1. So I have x over 1 is sine of this angle. Are you with me, guys?
Yeah.
Yes, right? So basically, what is sine inverse? It means apply sine to it, and you'll get the ratio of opposite to hypotenuse equal to x. And you see, I can draw many different triangles. It doesn't matter. The ratio, they are all going to be similar triangles. The ratio of opposite to hypotenuse is always going to be x. So for example, I could have made this x squared and the hypotenuse equal to x. I could have done many such things, but it doesn't matter. Ratio is the same. So I just fix at a convenient value where opposite is x and hypotenuse is 1. And that makes, by Pythagorean theorem, the remaining side is 1 squared minus x squared square root. So the remaining side is 1 minus x squared. So if I take cosine of this angle, think about it. Cosine of this angle is adjacent over hypotenuse. So it's root 1 minus x squared. So I can replace the denominator by a much nicer looking expression, which is root 1 minus x squared. Are you with me?
Yep.
If you are with me, your goal now is to find the derivative of cosine inverse. Go ahead, calculate cosine inverse, and then we will work through it. I want the derivative of cosine inverse. Yes, Abdul, you're correct. So here is how it works. Very similar, right? I always set y equal to this expression, right? And I can take cosine of both sides. By the way, notice that you can use geometry. It would be, by geometry, it must be 1 over minus sign, if you think about it. So cosine of y, I think Melissa understood definitely last lesson what I was talking about, right? So geometrically, it's clear it should be 1 over the derivative of cosine of y, which is minus 1 over sine of cosine inverse.
Adjacent over hypotenuse.
Isn't it going to be negative 1 over the square root of 1 minus x squared?
Right, it's exactly right. But make sure that you understand how you said it. I just understand that I end up with minus 1 over sine of cosine inverse of x. Now cosine inverse of x, it's an angle that if I apply cosine to it, I'll get x, right? So if I draw this triangle, it's a symbolic triangle. Adjacent is x, hypotenuse is 1. And the remaining side is 1 squared minus x squared square root, right? So I know this. So if I apply sine to it, I will just get this divided by 1, which is just root of 1 minus x. So you have this expression, yes?
Yes.
Yes.
Professor, is it correct if you just leave it as -1 sine inverse cosine x?
No, it is correct, but it's kind of messy. You see, this is an operation that's significant mathematically. Yeah. In other words, you want the formula as neat as possible. So you were correct, right? But I want you to realize first thing is I want you to understand that sine of cosine inverse x can be actually solved in terms of algebraic expression. So it's neater. Right, so and then I want you to find me the derivative of tangent inverse x, please. If you have to go, guys, we're technically done, but I would like to finish today's lesson completely.
I'm in. I could continue.
Good. So let's try to finish today's lesson before we stop. Find the derivative of tangent inverse, please.
Oh, come on. Okay.
I have 1 over secant squared y
Right, brilliant. That's very good.
Is also gonna end up being 1/1 plus x squared, I think.
That's good. That's good, right? So here is what you end up having.
Oh, there it is. Okay.
Yes, here it is. You see it? So a y prime. So I mean, it's all the same procedure, right? You take y equal to this. You apply tangent. You take the derivative of tangent is secant squared. So it's 1/secant squared y. And then you have to calculate secant of tangent inverse of x, and then you have to square it. So if I put tangent inverse here, then I know its opposite is x, adjacent is 1, and then hypotenuse is 1 plus x squared. So secant squared of tangent inverse is root of 1 plus x squared, which is 1 plus x squared. And I get 1/1 plus x squared. It's pretty simple, right? You see how the formula goes. Yeah. Great. And then, you have one for secant and whatnot, but, and then I'll skip it for now. Let's, you see, I want you to do the following, guys, okay? I have a few other examples, but let's do C. I want you to take the derivative of cotangent inverse t plus cotangent inverse 1/t. The derivative of cotangent, you can use it's minus 1/1 plus x squared. You verify it later, not today. I mean, today, take this as given, right? The derivative of cotangent is this, and use it to, and tell me what's the derivative of h of t.
This is on your website, right?
It is on my website, yes.
Okay.
Did you put it on already?
Of course, I emailed at least an hour ahead of time. I put it on. Today I was able to finish it quicker.
I see it. Okay.
All my lecture notes are always on my website, starting from the time we stopped meeting.
Yeah. Okay. Would you add both of them at the end?
Well, we will see what I do. I want to see what you will do. Okay. And so for C.
Okay.
Aren't they canceling each other?
That's a good question. Are they not? But then you mentioned that you see my notes.
I don't see your notes. I didn't say that. I have my notes, but you didn't do that in the videos.
No.
So.
Okay. Are they canceling each other? If they are, well, basically your question is to find the problem is to find the derivative of h of t. Okay. I mean, when you're saying canceling, maybe you're saying something very interesting. You have to be more specific. What do you mean canceling each other?
Professor, can you change it to cotangent inverse t plus 1/t?
Well, I mean, you should know how to answer this.
I mean, would that help in solving?
No, I mean, you see, you cannot just invent rules. Either this is true, what you said, either I can move the cotangent inverse out, or you are just trying to make your life unjustifiably simple.
No, not taking it out, just making it cotangent t plus 1/t in parentheses.
But why? Why would that be true?
That's one of the rules we learned.
No, it's not a logarithm. I have not learned any such rules.
No, if it was tangent t plus 1, that would be the same thing as tangent t plus tangent 1.
Well, so you're saying that h of t is what? H of t, you're simplifying it. What are you saying it is equal to?
It is inverse cotangent with the parentheses t plus 1/t.
Yes, and that's not true.
That's not true?
Yeah, so that's what I'm saying. Where did you put such rules? you cannot, guys, you see, you will make infinitely many mistakes if you are going to invent rules. You see, it's not arbitrary. You see, I know why I can make logarithm of a product the sum of the logarithms. It's not arbitrary to me. Okay, so that's what you mean. You have to know your function, just like when you get to know people. You have to know them very well. Then you don't make mistakes. You can try to find the derivative even directly. It's up to you how you work it. But I want to know what's the derivative of h, please. How are we doing?
Professor, unfortunately, I do have to go.
All right. Okay. Take care. Take care, Joel. And
I'm happy I came today.
okay, happy to hear from.
We'll keep in touch. Bye, guys. I'll see you
Take care.
Thursday.
Right. All right. Melissa wrote t to the 4 minus 2 over 1 plus t squared. Melissa. Thank you, Melissa, so much for writing it, but you are wrong.
Oh my god.
No, of course it was. Another thing I'm upset, Melissa, is I don't see your face. I miss you. I actually miss all of you guys, but you don't show me your faces. Daniel, I haven't seen your faces. Daniel McKenna, the other Daniel. David, I haven't seen your face. Sarah, I haven't seen your face.
I have an excuse, Professor.
Yeah, you do. But it's okay, you know. And you, Zina, how are you feeling? Many of you are injured.
Actually?
All right. So are you still working on it? It's not such a hard thing. You see, what's the derivative of cotangent inverse? It's simply minus 1 over, well, of 1 plus whatever inside of cotangent squared. Yes?
Yes, correct.
Yes. So let's look at it together. Here is C. I don't want to reveal too much, right? So the derivative of cotangent inverse is minus 1 over 1 plus t squared. Now in the other cotangent we had right, we had now plus cotangent inverse of 1 over t. So the derivative will be 1 over 1 plus 1 over t squared. It's whatever with the minus here, times the derivative of 1 over t. It will be another minus. It will be minus 1 over t squared. So minus minus makes it a plus. And then I can multiply the t squared through, and I get minus 1 over 1 plus t squared plus 1 over t squared plus 1, and I get 0. I got 0. What does it mean, guys? The derivative of the function is 0. It means the function is what?
Constant.
Constant. It's not only a line, it's a horizontal line. So right away when you think, okay, that if there is no dependency on t, is that reasonable? Can it happen? So it's a constant. Here is how you interpret it. Very simply, look at it. What is cotangent inverse of t? Right. So I draw a triangle. I draw this angle, which I label as cotangent inverse of t, and I draw this angle, which I call theta. So if one way to draw the triangle is cotangent inverse of t means that the ratio of adjacent over opposite is t. So this is t, this is 1, correct? I'm not really interested in the hypotenuse. I can describe this angle as what? This angle I can also describe in terms of cotangent inverse, right? What is that? It must mean that this is cotangent inverse of 1 over t. Do you agree?
Okay.
Do you understand why? Because I can call this angle in terms of cotangent inverse by looking at the ratio. 1 over t adjacent to this angle over opposite will be cotangent inverse of this ratio, right? 1 over t, it will be, so cotangent inverse of 1 over t is this theta. But what do I know about the sum of those angles? This is 90 degrees or pi over 2, so this must also be pi over 2. So I know that cotangent inverse of t plus theta is equal to pi over 2. You see, geometrically, I know that cotangent inverse of t plus cotangent inverse of 1 over t equals to pi over 2. And by the way, cotangent inverse of 1 over t, I could have labeled as tangent inverse of t because it's this over that, right? So cotangent inverse of 1 over t actually happens to be tangent inverse of t. You can derive formulas this way by mere logic, but you cannot invent a formula where you have cotangent inverse of t plus 1 over t. Good?
Yep. That was
okay. So that's how you get to know them. First of all, logically, this symbol means to me something. I think of cotangent inverse of t. I right away think, put it inside of cotangent, and you get t. If you put this inside of cotangent, what do you get? What I'm hovering my marker over, cotangent inverse of 1 over t. If I put it inside of cotangent, what will I get?
the same.
Careful. Same is very ambiguous. What's the same? If I take this expression,
Okay.
and I put just that part into cotangent, what do I get? 1 over t, Melissa, correct. I get 1 over t. It basically means similar to logarithm, but just a different way of writing it, right? Logarithm is inverse exponential, for which you just have this separate symbol. But really, what this means, place it inside of cotangent, and you get what's here. It's the undo. Okay? So there are many more of those examples, let's say, that you might want to, for example, can you tell me what's secant inverse of x plus tangent inverse of 1 over root of x squared minus 1? Maybe, and afterwards we can call it a day. Just tell me what this number equals to. It's a number. What's secant inverse of x? All right, Zina, go. I hope you're feeling better. It was nice to know that you were present here in spirit. And if you're still staying here with me, guys, maybe last question, what is the exact value of secant inverse of x plus tangent inverse of 1 over root x squared minus 1? See if you can figure that out. whenever you're dealing with trig functions, like inverse functions, you right away think of the right triangle. That's a very simple advice. So draw a right triangle for, say, secant inverse of x. That seems simpler than to deal with this, right? What's the right triangle for secant inverse of x? And fill out all the sides of the triangle and the hypotenuse. No, but don't give up. That's not how it works. Draw the right triangle, see what is secant inverse of x, what can you say about the right triangle, and see what we can get from it. Yeah, as you think, I'll just go turn on the light. David, you're there. Sam, Daniel, what are you doing?
Yeah. Stuck at the triangle.
Thinking is great. Sorry that I hurt you. I just was worried. Draw a triangle and write what are the sides, all the sides. What are they? Well, let's see. So if I draw this right triangle and I place this as secant inverse of x, it means that if I apply secant to this angle, then I get x, which means hypotenuse over adjacent is x. So I can label the hypotenuse as x, adjacent as 1. And then by completing the triangle, I know that the remaining side is root of x squared minus 1. Are you with me, guys? You see that the remaining side is root of x squared minus 1. Mm-hmm. Now, what is, describe the angle theta. What is this theta? You see, so I have, this is always pi over 2. It's a right triangle. This is secant inverse of x. Give me some descriptions. I just want to give me a description of this theta. There are many descriptions in terms of this triangle. What is theta?
Some angle that adds up to 180 when added to.
Yeah, but I want you to use the language inverse something. This would be some inverse trig function of what? So, for example,
cosecant inverse.
Let's play around this game, okay? I want you to label theta in terms of secant inverse something. So what is theta as a secant inverse? We know that secant inverse of x is x over 1. If I want to describe theta in terms of secant, in other words, what secant maps it to? So secant inverse theta equals to secant inverse of what?
A regular secant?
No. It's yes, Melissa. It's of x over root x squared minus 1. So it will be secant inverse of x over root x squared minus 1. Because look at it, secant of this angle means take hypotenuse divided by adjacent, right? So it would be secant inverse of x over root x squared minus 1. I want you to give me a description of this in terms of inverse cosine. What is theta as an inverse cosine? You see, guys, that's what I'm trying to make you realize. You see, you look at it as just labels, but it's a description. What is theta as inverse cosine? So Melissa says as inverse cosine, it is root x squared minus 1 over x. And you are absolutely right, Melissa. So theta is cosine inverse root of x squared minus 1 over x. What is theta as inverse sine? Theta as inverse sine. It is, no, it is not x. Theta as inverse sine. So Melissa corrected. It's not x, but what is it? Exactly. So it's inverse sine of 1 over x. And as inverse tangent, what is it as inverse tangent? As inverse tangent, it is 1 divided by root of x squared minus 1. So in other words, theta can be written as inverse tangent of 1 over root x squared minus 1. Regardless, secant inverse of x plus theta always equals to pi over 2, because the remaining side is pi over 2 as well, and they all add up to pi. They all add up, I'm sorry, to pi. So really, instead of taking the derivative of this expression, I'm really taking the derivative of pi over 2, which is obviously 0. Let me ask you before you go, maybe one more question, guys. Could you please tell me, so I'll write it over here. So what is...
I'm gonna have to go, but I just wanted to say thank you for the.
Oh, nice to see you. And if you have to go, no, don't feel compelled to stay any longer. I'm really happy that you came. I hope you're beginning to feel better.
Yeah, I'm happy I came too. I feel like I needed to hear all this. Thank you so much.
Right. Take care. Guys, before we go, tell me please what is cosine inverse of x, right? Cosine inverse of x plus, let's see, plus sine inverse of I think what is it, of 1 divided by root of 1 minus x. What's it? One second. Give me a moment. One second, guys. I'll be right back. Let's make it this way, right? So what about cosine inverse x plus sine inverse x? Let's see if what would we say? Damn it. What is that? All right, Batel, take care. Have a good one. Zero, no.
Would it be x plus 1 over?
So how can you solve it quickly? Hopefully I haven't made a mistake. You know, I'm a bit tired, but how am I coming up with such formulas? I'm not doing anything very magically complicated. I'm just figuring out what's the relationships between angles in a right triangle. So when I see cosine inverse of x, I right away imagine what? I imagine a right triangle. I'm sorry, I drew it so poorly. So this is the cosine inverse. I'll write it as simply c minus 1. And then I can write this as x, and this as 1, right? Because what way do I get? What way can I have ratio of adjacent over hypotenuse equal to x? So if this is 1, so it's x over 1. Now, what is the remaining side? The remaining side is root 1 minus x squared. Yeah. And so I look at it, okay, cosine inverse of x, and I can also get sine inverse of x. This would be here S inverse, sine inverse of x, because x over 1. So you can see that the sum of those two angles is pi over 2. So cosine inverse of x plus sine inverse of x happens to be pi over 2. Okay? So yes, I guess we call it a day. Have a good one.
All right. Thank you, Professor.
Sure.
Thank you.
Yeah, nice to see you, Magnus. So at least to know that you were here. Bye, Daniel. Oh, Melissa, you're funny. It's too bad you decided to hide today. Yes, thank you. I'm butchering your name. See, what? God damn it! How do you pronounce your name?
Yisheng.
Yi Sheng. Yi.
Yeah.
It's because I never read X as Sheng. It should be CH or something. Yi Sheng, right? Well, but
Yeah.
I wanted to say hello to you, but I was afraid that how do you pronounce your first name?
I was afraid to speak.
No, don't. Why are you afraid to speak? Speak, right? And maybe show your face. I would be happy to see you.
Okay.
All right.
Thank you.
Take care, guys.
Thank you. Good night.
Good night. Don't hide from me, guys. Bye.
Bye-bye.
Thanks, Professor.
Yep. Take care.